Hi, this is CrossDot and Nabla. This is the first video in a multi-video series in which we'll be covering the entirety of Calculus 3. The note sets will be set up into 4 different chapters. So chapter 1 is going over, in general, what Calculus 3 looks like, what each of its components are. So that's going to go over things like the cross product, dot product, going over lines in space, length of curves, curvature, right? And then we're going to go over functions of multiple variables. So that's going to go over like partial derivatives, chain rule, functions of multiple variables, max and min problems, Lagrange multipliers, and then we go to double and triple integrals, and then we go to vector calculus. And part of what I think is important to take away from this intro video, I guess, is understanding that Calculus 3 is not just a scaling up of Calculus 1, where instead of working in one variable, you have multiple variables you're considering. I think there's a lot more nuance that's attached to it, specifically with learning a lot of new skills. I think once you get past Calculus 1 and 2, there's an emphasis more on understanding the base conceptual of why does this theorem apply when does the situation apply to what. And I think like building these like very strong basics through these videos will help massively. And a couple of things about myself. I'm a junior in high school, and I just took my Calculus 3 course this past year. And I wanted to work on this project for myself because I'm not perfect. No one is perfect. And I think going through these videos, making them will help me become a better student in understanding Calculus 3 as well. So today our first video is going to be on vectors in a plane and in 3D. So we have 2 different approaches we can really work with. We have a geometric and algebraic approach, but we can just define some terms first off. So a scalar. A scalar is just a quantity defined by magnitude. So what that means is anything that has like a value attached to it, right? So like, for example, it could be like 3 square root of 2 pi, like, I don't know, like 1,000, right? These are all scalar quantities because they just have a magnitude attached to it, right? However, a vector has a quantity that has both a vector is a quantity defined by both its magnitude and direction. So for all of these numbers, they don't really define direction, right? Like 3 root 2 pi, direction. So like, for example, like this ray from tip to tail is a vector because it has a magnitude. You can measure the distance of the ray, or you can measure the distance of the line, and in what direction it's going in. It's going in north, south, east, west, like what angle theta, right? We can attach to it, right? And that kind of ties into the other two words at the bottom, magnitude and direction. This just refers to like the length or value of a quantity. And I feel like that's kind of self-explanatory when we think of something like, oh, I have 3 apples or 5 gallons of milk, right? That's a magnitude of a quantity, right? We're just saying the number attached to it, right? And direction, it's like, this specifically refers to a vector where a vector is pointing in time. So like, for example, these 2 vectors right here, this vector and this vector, they're pointing in different directions. This one's pointing in the east direction. This one's pointing like northeast. These have different directions and thereby going to have like different angle measures, right? So that's another thing to consider and keep in mind when we're working through these properties, right, of vectors. So first off, this one, it kind of seems obvious, but it'll help us have a better understanding of what vectors do look like. And it's just the statement that says that the vector u equals the vector v if they have the same magnitude and direction, right? So like, for example, if I drew a vector like this and a vector like this, it's not perfect, but the idea is that you would imagine that this theta, they're equal to each other, so like they're rotated the same amount off of the x-axis, right? And in fact, they have the same distance or the same magnitude, right? So we can say this is x, this is x. So we can call these both magnitude x and they have the same direction. Then we can say that this vector right here, we'll just call that u, is equal to this vector v. And then we have the 0 vector. This is where it says that the vector is 0 and 0 plus u equals 0 plus u equals u. This is kind of similar to scalars, where we can say that like anything plus a number just equals that number, right? So there are some similar properties with vectors and scalars where we can like look at that as well and understand why that is, right? Because well, we'll actually get to that later with the algebraic approach. And then for a negative, when you want to take the negative of a vector, all you're really doing is flipping the direction, right? So for example, this is my u right here. My negative u will look like that, right? So I'm just flipping the direction of the vectors. Yeah. And then we have a scalar multiple of u equals cu. So this is kind of, again, like saying that we have like a number like 3, you multiply by n, you just get 3n, right? You're just multiplying n to get something that's 3 times greater, right? So to illustrate that right here, we have this vector. Actually, let me make that smaller real quick. We have this vector, and then we have this vector. They have the same angle. They're the same angle theta, but this is u and this is v, right? But v, in fact, is equal to twice as much as u. And that's kind of referring to like the scalar property, right? So it's like another example, like for scalars, I'm trying to illustrate this with scalars to vectors as like a good comparison, right? Saying that like 4 equals 2 times 2, right? And that seems obvious to us, but when we're working with vectors, this process of like scaling something up makes more sense. And we'll actually get to a concept where you have to solve for a vector which the magnitude of it is going to be 1 later on in this. Some other properties of vectors, you can actually add them up. And the way to do this is something called the tip to tail method. I mentioned this a little bit earlier. So whenever you're drawing a vector, this is something we did in geometry, right? We always start off with the tip, the bottom of it, the tip, right? And then we have a tail going out, and this is u. And then I'll label this new one as the tip of v, right? And v goes all the way out. We'll just highlight it. And we get to this endpoint, I'll just label that in blue. However, we can also just start off with the red right here. We can start off with the red right here, go out, and then line up to get to there, and then u. So this kind of goes back to another like property that we mentioned earlier. It's kind of like the commutative and associative properties of vectors. Whenever you add them up, they're the same thing, right? So that's very, very helpful for us. And oftentimes, if you have just like straight lines, they're going to make parallelograms. Yeah. So for example 1, we want to express w in terms of u and v. And one thing I'd like to mention before working on this is when we're doing these problems, oftentimes you're going to be seeing this in bold. I know it doesn't show well on my screen, but there's going to be oftentimes in math textbooks where they're going to write it like w like in bold, which in essence just means W like this. The reason why the textbooks write it in bold instead of an arrow, they have like a definition part in the beginning of the textbook saying like what each symbol means, right? They do that just to save money. So these two, I'm just gonna write W in bold so it's easier for you guys to understand. The W in bold just equals the W with the arrow, right? So the question asks us to express W in terms of U and V. So, let's see. How would we work through this, right? So I noticed that we have the starting off point right here, and we end up here at the end, right? I see that when we add up U and W, we go from here to here, we go from here to here, right? But we know that with the V, we end up in the same spot, right? And what we did earlier is that kind of same idea with this, right? And in that case, it would be U plus W equals V. Looking back up here, we said that U plus V, the vectors, adding them up, right? The vector U plus the vector V, tip to tail, would get us V plus U. We got to that same result, right? And in fact, what we can do is we can also just subtract vectors and get in the opposite direction, right? So we can say that W, the vector W equals the vector V minus the vector U. And we can look at this and it'll make some sense, right? So if I go in the direction of V right here, and then go down like this, I get W from that. So it's the same magnitude, same direction. Pretty cool. And then example 2, drawing W, where W equals V1 plus V2 plus V3. I'm going to give you guys a second to do this one because I think this is one where you just have to look at it and basically just do tip to tail like we did in these previous examples right here, right, with the adding vectors. Pause the video if you want to work on this. Okay, so we're going to start. I usually like to start off with whatever it says number 1 is, so we'll just do that. So this is V1. Again, it's in bold, so I just write it out just for my clarity. This is V2, and that's V3. Then we got our final result, right? Pretty cool. Now, go on to example 3. Mark pushes on a post in the direction south 30 degrees east with a force of 60 pounds. Dan pushes on the same post in the direction south 60 degrees west with a force of 80 pounds. What are the magnitude and direction of the resultant force? Okay, so a couple of things we have to learn with these types of problems is understanding what the heck does south 30 degrees east mean, right? So south 30 degrees east, let's go draw our coordinate plane. Actually, I can use a ruler instead. It makes it easier for you guys to actually do these types of problems. What south 30 degrees east means is when we have these types of problems, it's gonna be east, north, south, west. So when you say south, we're gonna start off in south, right? So go down here. And we're gonna go 30 degrees east. So it's like this. So we're 30 degrees east off that with 60. That's the magnitude of it, right? So we have the direction and magnitude of the vector. And we have the same force south 60 degrees west. So we go south first. You see south right here. And then we go 60 degrees west. And although this isn't the best drawing, I hope the illustration makes more sense with this. The magnitude's 80. The magnitude here is 60 for Mark and Dan, right? And what I can do now is we can do tip to tail actually and add up these two vectors, right? So we go like this. And that's going to get us 80 again. And then we get 60 right there. And yeah, so this is what we have now for this. And if you can tell, actually, we can use the Pythagorean theorem for your 60, for your right triangles, because this is a Pythagorean triple, actually. So it's going to be 60 squared plus 80 squared. Because I'll just illustrate that like this, right? It's going to get you to x squared. It's going to be 10,000 equals x squared, so x equals 100, right? And then what we have to do now is we have to solve for the resultant angle. And what we have to do for this is actually have to add up the vectors. So it's going to be m plus d, and this is just going to get us 60 cosine of 300, 60 sine of 300, plus 80 sine 210. Oops, not sine, it should be cosine. Oops, let me just need a smaller eraser for that. $80 cosine 210, 80 sine of 210. And then when you add up these two, you plug it into your calculator, you would get negative 39.28, negative 91.96. And we just do tan inverse to solve for that. And we know it's in the third quadrant, so we don't have to worry about it. And then you would get south 20 degrees west as your answer. So yeah, that's how you would do example number 3. And example number 4 is kind of along the same lines. Take a moment or so to look at the problem while I'm just setting up the angles. And if you'd like to pause the video to try this on your own, feel free. Okay, so we're gonna go back to our directions: east, north, south, and west. A ship is sailing south to 20 miles per hour, so we'll just draw the vector like this. That's gonna be the ship. And then we have the man walking west at 3 miles per hour. So like this, so that's the man. And then what we can do is add up the resultant vectors like we did before. So that would just be another tip to tail, like that. Actually, it's not. It's going to be more accurate. Like that's good. Sorry about that, guys. And then same thing, we're just gonna draw this down like that. And now we have our new final location, right? What we can also do is say that our vector is constant in both cases, right? In either the x or y, right? So we can say that the vector of the man, you just say that man is a vector equal to negative 3, 0, because the man's going 3 miles per hour west. The ship is going 20 miles per hour south. So like that. We add up these two vectors, we would get m plus s equal to negative 3, negative 20. And as you can see, that's where we end up right here. We can draw this out. And then we want to figure out the resultant angle from here. So this is just going to be right triangle trig. So this is going to be 3. This is going to be 20. So we have to do tan inverse. So tan inverse of 3 over 20, which would get us south 8.53 degrees west as our direction. Our magnitude would just be doing 3 squared plus 20 squared equals x squared. So that's 9 plus 409 equals x squared. of 400, so that's me 409 equals x squared, take the square root. Then that's like 20.1, top of my head. We can calculate 20.22 as the relative magnitude and velocity to the surface of the water, right? These are a couple examples. Also, don't forget to add the units. And then the second approach that we mentioned earlier is an algebraic approach. So if we have our vectors on like a Cartesian coordinate plane, and in layman's terms, a Cartesian coordinate plane is the coordinate plane you've probably been seeing for most of your life since Algebra 1 is just the XY plane. We can plot vectors in this, like this, like this, like this, right? You can do that. You can add them up, right? So we can say that if the tail ends at the origin, so the tail ends at the origin, then its head will end at some point like this. And we said that the vector, this is in bold, we write the arrow, is this, right? And if you think about it, it kind of makes sense, right? Because if we start off at the origin and we go off to some point in space, we have to cross some arbitrary delta x, some arbitrary delta y, and oftentimes in this class, we will be going into the third dimension. You'll be some arbitrary delta z, right? So if we were to do like a line of that, it would be delta x minus 0, delta y minus 0, delta z minus 0, because we're doing final minus initial, right? And these in this u1, u2, u3 are called components of u. These are the parts of it, right? So the amount you walk in the x, the y, and the z direction are going to be your components that make up your vector as you move away from the origin, right? So like, let's say, for example, just draw like a kind of like a rudimentary XYZ plane. And oftentimes you will have to sketch this in your calculus 3 classes. Imagine we have someone who is at the origin, right? We'll just say I was red dot, right? They walk 1, 2. They go across 1, 2, 3. So they're here now. And then they go up, like, let's just say 2, right? So they went 1, 2, 3, like that. You could also just draw their triangle like that. And it's a little bit janky, but you can see a little bit how that would look, right? So in this direction, we're walking 2. In the x, we're walking 2. The y, we're walking 3. The z, we're walking 2, right? So that's the way you would write the vector, like that. And another cool property of vectors we talked about earlier is u equaling v, right? The vectors equaling each other. IFF. What this means, this is like proof speak in calculus textbooks. It means if and only if. So what that means is you have components that are necessary, but if only one of them exists, it's not necessarily sufficient, right? So in this case, it would be saying the vector u equals the vector v if and only if u1 equals v1, the components in the x and y, right? u1 equals v1, u2 equals v2, u3 equals v3, right? So, for example, this is not equal to this vector. Why is that? Why does that mean, you might ask? Because according to this definition, the vector u equals vector v if and only if. I'll write that out. If and only if u1 equals v1, u2 equals v2, and u3 equals v3. So let's see. u1 equals v1, true. u2 equals v2, true. But u3 does not equal v3. So then, therefore, we cannot say that these two vectors are equal, right? And if you were to graph that out on the Cartesian coordinate plane, that would make sense, right? And then we have more vector goals from earlier. Instead of doing the tip to tail, you can also add up the respective components if you know those. So in this case, if we know that u1, u2, u3 plus v1, v2, v3, you can just add those up like this, and you get your new vector. And then this is like the identity properties, like -1. You multiply everything by -1. Just be like this, u2, u3, and then it all comes inside. And you can pull out this as well. And then 0 equals 0 u. It's just gonna all be 0, right? And a lot of these are kind of self-explanatory if we go back to like scalars, like I mentioned earlier. So like for example, if you multiply something by -1, like for example, if you multiply a number n by -1, it just becomes -n, right? So it just flips the direction of the number line, right? Like if I had a number line here, I had 0, I had, 2, 1, -1, -2, whatever, right? I have my point 2, 1, 2. If I had a -2, it'd be -1, 2, like that. And we're just flipping the direction of it, right? The same idea for vectors. And then for the 0 property, that one is kind of intuitive if we remember what u1, u2, and u3 mean. It's that we're making steps in each of these directions, right? So if we're not making any steps, it's just going to be 0 for its magnitude also, right? That's another thing to keep in mind as well as we're going through these problems. And a theorem that's going to be very applicable for vectors are the ones below right here, where we have for all vectors u, v, and w, and the real numbers a and b. This is just going over the commutative and associative properties for vectors. I'm just doing this real quick, because regardless of how you add them, it's all going to size the same, right? And for some of them, like for example, u plus -u, it's kind of like saying that 2 plus -2 equals 0. Seems kind of obvious to us for scalars, but for vectors, this is going to help us in solving these types of problems. This is another commutative property, associative property right here with this, distributive property right here, distributive property, and then an identity property. And all these can tie back to scalars, right? So there's a couple more formulas right here that are extremely important to know for vectors in general. If we had a vector in 2 dimensions, say we got something like u1, u1, u2, we can just call that u, the magnitude, that's how you write magnitude in calculus, magnitude of u would just be the square root of u1 squared plus u2 squared. However, now that we're in calculus 3, we're going to be operating with a lot of 3D vectors, right? So the way to explain how this would work is, again, we have our x, y, and z plane. We go in some direction in some direction x, we go in some direction y, and then we end up in some direction z. We're going to make 2 right triangles actually. So the first right triangle you're going to see is one right here with your u1 and your u2 components. So you want to solve for the hypotenuse of that. We just get that from right there. However, you want to solve for the height of this, you have to use the Pythagorean theorem again. So whatever you have for this right here, our hypotenuse, this is going to be another leg of this. This is going to form a right angle from the side. And we can do like a side view of it actually. So what this is saying is that this right here, this side length right here, is going to be u3, and this is the u1 plus u2 squared, like that. And then you want this x. You want, well, actually, no, let's not call it x, because that x is something else in this case. Let's just call it the d, right? The d for magnitude, right? We just use Pythagorean theorem, and we say that the square root of u1 squared plus u2 squared, square that whole quantity plus u3 squared equals d squared. So then we have this and this cancel. It's going to be u1 squared plus u2 squared plus u3 squared equals d squared. Just cancels. And that's how you would derive that for this in 3 variables. Another property that's kind of similar to this is c, this right here, the magnitude of c times the vector u equals this. This kind of makes sense if we think about, like, if we're multiplying something by 3, right? Like 3 times this vector, right? We do 3 to get 3, 3, 3. The magnitude of this would be just 3 squared plus 3 squared plus 3 squared. That's just root 27, or 3 root 3. But if we had this originally, we just had it out like this. It would be 3 times 1 squared plus 1 squared plus 1 squared. That just gets us 3 root 3. These two results are just the same thing. So you can just, so if you see like a common factor between all of them, like for example, if you see something like 2, 4, 6, what you can do as a common factor is just pull out the 2. And it saves a little bit of time just like doing the annoying arithmetic. So, I mean, in this case, it's kind of easy to do. So it's me 1 plus 4 plus 9. So it's 2 root 14. And we could still do it like this, where it'd be 4 plus 16 plus 36. That's root 56. You can pull out the 4 as a factor, but it just saves you time. Okay. Example 5. Let the vector u equal -1, 5, and 2. Find the magnitude of u and -3u. Also find a vector u in the same direction as u, but with a magnitude equal to 1. This is called a unit vector. Okay, so we know this is our vector, and we want to plot for the magnitude u, right? So we know the formula for solving for the magnitude of a vector, just the magnitude of the vector itself, equal to right? So we know that so we're just going to do this, right? We're going to do 1 squared plus 5 squared plus 2 squared equals the magnitude of u squared, which is just going to be 1 plus 25 plus 4, which equals root 30. So we solved for the magnitude of this. And then -3, we can use that constant rule we learned earlier. We want to take the magnitude of the constant on the outside, right? And put root 30 here, because that's what we derived above from here. And the absolute value of this would be 3 root 30. Get our answer. Now you might be asking, what happened to the -3? Well, if we're solving for the magnitude of something, the magnitude is similar to the absolute value, in which regardless of the direction, or like the positive or negative, regardless of the sign, essentially, your value is always going to be positive, right? Because it's the distance from 0, right? And if we look back at the formula, that's what it's getting at right here. This is only the one bracket. The double brackets are referring to the magnitude. And then solving for a vector u hat with the same direction as u, but with magnitude equal to 1. This is called a unit vector. So a unit vector is just a vector with magnitude 1. And the formula for this is a really useful formula to know in calculus 3, is going to be like this: u1, comma u2, comma u3 over the magnitude of u. I don't want to write it out in full, but essentially what's going to happen is that this is going to give you a vector of magnitude equal to 1. And what we can do is just have it set up now. We can just do 1 over root 30. We have 5 over root 30. 2 over root 30. And then this is our u hat. Other types of unit vectors you'll be seeing in calculus 3 are things like I hat, j hat, and k hat. And those are relatively similar to this, where we're working within a Cartesian coordinate plane. So your I hat just refers to a change in the x direction by 1, j hat for the y, and then the k hat's for the z component. And for this, the u hat's the same idea, right? But it's referring to the specific vector. So we know that u hat equals negative root 30 over 30. I'm just going to simplify because it makes my life easier. This is going to be 5 root 30 over 30. This becomes 1 over 6. 2 root 30 over 30. This becomes 1 over 15. And I'll rewrite that again. Our u hat equals negative root 30 over 30. Root 30 over 6. Root 30 over 15. And then if you were to square everything and take the square root of it, like we did above here, you get a distance of 1, or a magnitude of 1, excuse me. And then for this last example, we have this. A plane is flying north-northwest in calm air and at 400 miles per hour when it encounters a horizontal crosswind blowing southeast at 60 miles per hour and an updraft wind blowing vertically upward at 40 miles per hour. What are the resulting speed and direction of the plane relative to the ground? So a couple of things before I'll let you guys go. To understand what north-northwest means, we'll just draw another coordinate right here. East, south, northwest. We have northwest, we have northeast, right? We also have north-northwest, so in north-northeast and northwest-west. And the way you're going to be reading this is you're reading this halfway between north and northwest. So northwest is like right here, and north is like right here. Northwest is going to be right here. So like, for example, if I were to say like south, southwest, southwest is like this, south is like this, something in between is like that. Does that make sense? So in this case, you would solve it like that. And for this problem, you would probably use like cosine and sine just to make your life easier. And for this, you would probably graph this out too. So if you guys like to take a moment to pause the video and try this problem on your own, feel free to do so. All right, let's start off. We can understand that north-northwest, right? So it's gonna be the second quadrant. Northwest is 135. That's 45 from 90, so 22.5 plus 90, so it's going to be 400 cos 1.112, 400 sine 1.112, 0 for the plane. And then we have the horizontal crosswind at 60 miles per hour. So the wind goes southeast, 60. So it's going to be southeast, it's like 315 as our angle. And if you guys think about it, that makes sense, right? Because southeast is halfway between south and east. It's 90 degrees between the two. So the average, that's 45. You have 275 plus 45 gets you 315. And then we have horizontal. And then we have the wind vertical equals 0, 0, and 40. Then we just add up all these respective vectors together, and you can use your calculator for this. It's not the end of the world. This is what I got. For the sum, I'm just going to call that R. For the resulting vector, you take the magnitude of it, and I already did the math ahead of time, and I got around like 347.64 mph. So we got the resulting speed. The speed does not care about the direction, right? The velocity would, but the speed wouldn't, because it's just the magnitude of the velocity. and the direction of the plane relative to the ground. So in this case, we have the horizontal, and then we have the vertical as well. So it's kind of like what we did earlier above in this example right here, right, where we did like the right triangle to solve for the magnitude. But this time we're gonna use the angles instead to solve for the angles now, right? So in this case, we're gonna use our x and y components to solve for the angle. Use tangent inverse of 110.64 over 32712. And the reason why I'm choosing this is because I'm going like this and I'm like this, right? And then I'm calling this is my angle theta. We don't know. This is going to be 110 approximately. I'm just giving spitball numbers for this. And then I want the opposite over adjacent from this, because we're going to do it in like the notation we did earlier. We're going to get north 18.7 degrees west. And then we also want our vertical angle that they wanted from above. And that's going to be like kind of the similar idea that we did earlier, right? So we know that this is 40, but we need the distance of the x and y components. So we have to solve for that. And in this case, we can just set it up like shorthand and then just plug it into our calculator. So it would be negative 110.64 squared plus 327.64 squared. And then you want the angle theta of this. Tangent inverse 40 over this entire quantity. The negative cancels out, so I don't want to write it. And then you would get theta to be approximately about 6.6 degrees above the horizontal. And yeah, that's pretty much how vectors in 3D and space work. This is the first video in a multi-video series. Like I mentioned earlier, this is the first video that we are posting. So it's a little bit longer because, in fact, it's covering 2 different sections of the notes. So that's going to be something to keep in mind as well. And yes, thank you for watching. This is Crossdot and Nabla, and I hope you guys have a fantastic day.